And thank you for the organizers for inviting me. It's really nice to be here. I had last year a chance to spend 5 months or so in Lyon working with Frank, and it was really a great time for me. I learned a lot, and yeah, I'm very happy to talk here in Frank's conference about the results that we proved. Yeah, so this will be a talk about finite-dimensional pseudofinite groups, about the classification of finite-dimensional pseudofinite groups of dimension at most 3. So that's no spoiler what we are going to do. And so I decided that from the very beginning I will give you the definition of finite-dimensional groups, because it's this dimensionality and finite dimensionality. It's these new concepts by Frank from 2020 or so. So maybe not everyone knows the definitions, but I should perhaps say, or I could, in terms of this talk, I could have done basically what Nick did earlier, just say that, okay, we are going to have this dimension on the definable sets of our group, which behaves in the nice way in terms of basically additivity and when the dimension drops. But anyway, so this dimensionality, to my understanding, was something that Frank invented so that there would be this uniform framework, uniform place where you can prove results or use techniques from stability, simplicity, or minimality, and pseudofinite structures, all of where you have things where you have dimensions. You have the Lasker rank, SU rank, or minimal dimension, or pseudofinite dimension. So in the general setting, it was defined on just some ordered abelian group. And so we are going to be interested in this finer structure of finite dimensionality, which I just defined for a group. So a group is finite dimensional if there is this dimension function dim from a collection of all interpretable sets in the models of the theory of group to natural numbers together with minus infinity, satisfying these 4 natural conditions. And so in my talk, so that was the definition by Frank, and in my talk I will include the definition of finite dimensionality, 2 properties from Frank's paper, additivity and fineness. So fineness just means that we are going to have the situation that the dimension 0 happens if and only if the definable set is finite, and additivity. So I didn't write what it means for a tuple to have a what is the dimension of a tuple over a set, but it is what you think it is. It's the infimum of the dimension of the formulas in the type of the tuple over the set. But all you have to know from that is that we take additivity so that we get the Lasker equality. So we have the situation that we have the dimension function dim from the collection of definable sets of our group to natural numbers together with infinity, so that the dimension drops when the index is infinite. We have the Lasker equality, and we know that dimension 0 means finite. Okay, and so important example in this talk is simple pseudofinite groups, so things like PSL2 over a pseudofinite field. And as we already know from Nick's talk, that's something that is super simple of finite SU rank, or probably people knew before. So general example is super simple groups of finite SU rank. So it's a generalization, this finite dimensional context. It's a generalization where you have many things from the super simple finite group theory still apply in the finite dimensional context, but you do lose some things like the indecomposability theorem that Nick was mentioning in the super simple setting. Okay, so I just essentially want to give one property of finite dimensional groups, which is something that we are using throughout our proofs, so all the time. And again, it's something that Nick essentially already mentioned. So one of the properties in the finite dimensional setting is that we have the ICC0, the chain condition of intersections of uniform definable subgroups, which is going to allow us to say that when we do these almost operators that was already mentioned in Nick's talk on almost normalizers or almost centralizers, we do get uniformity in the sense of the commensurability, which then allows us to say that the almost operator of a definable subgroup is definable. So let's go through that precisely. If we have a group G and then any subgroups H and K, we say that H is almost containing in K, written in that way if we have that the index of h intersected k in h is finite. And then similarly other way around, and then we call groups commensurable if they are both h is almost contained in k, and other way around. In the natural way, you define what does it mean to be uniformly commensurable. So we say that a family of subgroups of G is uniformly commensurable if there exists some natural number n, so that we know that this index between h1 and the intersection between h1 and h2 is smaller than n for any guys from our family. And then we define the almost normalizer, almost centralizer, and almost center just as you would do normalizers, centralizers normally, but up to commensurability. So the definitions are here. And again, you get to say when the commensurability is uniform. So of course you say that the commensurability is uniform, for example, in the normalizer of h in k, if there exists some m, some natural number m, so that when you have h and its conjugate to be commensurable, then actually this index between h and the intersection of h and hk is smaller than n. Okay, and so as I already said, it's not hard to see that in the finite dimensional context, we have this ECC0 condition, which I've written down here, so the chain condition and intersections of uniformly definable subgroups. If you wouldn't, then you would just get a family of uniformly definable subgroups, so that when you're looking at the intersections, you get the chain of dimension of G plus 1, and then contradict the Laskar equality that we just saw in the last page. Yeah. Sorry. That's exactly what I mean. Of infinite index in its predecessor. Yeah. Sorry. I thought that's what I said. Okay. And so then what easily follows is that when we have definable subgroups, then we know that the commensurability is uniform in the almost operators, and hence we have definable subgroups. Good. So that was the little things I wanted to say from the finite dimensional context that we are going to use throughout the proof, as you will see. Then I want to say 2 words about pseudofiniteness. So that's our kind of second assumption of our setup. Well, I do believe that people know what are pseudofinite groups. I decided to put it here anyway, since I want to say 2 words about the simple pseudofinite groups. But so first of all, an infinite group is pseudofinite if for every sentence in the language of groups, if G is a model of that sentence, there also exists a finite model of that sentence. And by was, of course, we know that that means that our group is elementary equivalent to an non-principal outer product of finite groups. Good. We saw some examples already in Nick's talk. I put some other examples here, so it's clear that the Z plus is not pseudofinite. Here we have our sigma saying that if the map sending x to x plus x is injective, then it's surjective. Of course, true in all finite groups, but false in Z. Then there is an example following from the completeness of torsion-free divisible abelian groups. We have elementary equivalence between R or Q and the outer product of CPIs. And then I wanted to put an example also that, of course, if you take an outer product of alternating groups, you get something that is definably simple, but not simple, because you can find a normal subgroup by looking at elements which are just kind of swapping 1 and 2 and 3 and 4 and keeping everything else fixed. And that's kind of suggesting that maybe we hope that the simple pseudofinite group, simple as a group, when I say simple, I mean always as a group, are just, so I say twisted groups of Lie type over pseudofinite fields. I guess I could have said Chevalier groups like Nick said in his earlier talk. So that's a result by Wilson. And what I mean by that, I say here, we denote a group of twisted Lie type over field F by XF. So this just comes from the finite group theory. So in finite group theory, we have the classification of finite simple non-abelian groups to be the alternating groups, and then the finite diminished products that you can forget. And then you have the 16 different families of groups of possibly twisted Lie type. So this X just means that it both specifies the Lie type and the Lie rank, so for example, PSL2. But if that's something that you know, that's great, and if you don't, it doesn't really matter in this talk. The point is that Wilson classified that simple pseudofinite groups are precisely those who are elementary equivalent to possibly twisted Chevalier groups or pseudo-finite fields, and then root and generalized this up to isomorphism. And so what is very important is that now what is this in particular saying? Well, it's saying, of course, that if you take a simple pseudo-finite group, its theory is super simple of finite as you rank, in particular finite dimensional, and also that the only simple pseudo-finite group of dimension at most 3 is PSL2 with dimension 3. So since we only have these finite many guys that we have to check the dimension, you can easily check that this is the case. But one point here is that this result of Wilson, it heavily relies on the classification of finite simple group, which is fine. And I mean, natural, once you have the classification, it's very natural to start to look at classification for the pseudo-finite case as well, using that. And so next, before going to our results, which are going to be without the classification of finite simple groups, I want to kind of give an overview what kind of results people have done using Wilson's result. So pseudo-finite groups in general, under some group theoretic or model theoretic properties, are quite well understood, and I think it really, really heavily relies on this Wilson's result. That once you have Wilson's result, then we can quite well understand pseudo-finite groups. So first, I have here this other result by Wilson. So I say that the soluble radical of a group, if it exists, is denoted by rad G. So soluble radical is just a maximal soluble normal subgroup. And of course, for a finite group, you have the soluble radical. And what Wilson proved, again using classification of finite simple groups, is that within the class of finite groups, the soluble radical is uniformly definable. So precisely what is said here. There exists an L-group formula such that the soluble radical. Oh, yeah, that's true. Sorry. Yeah. So that okay. So not precisely what is written in here, but precisely what I said. Yeah. Okay. So Wilson proved that there exists a first-order formula, so that for any finite group you have the solution set of this formula. And so from that result, you get that when you have a pseudo-finite group, you can consider this G bar. You quotient this G by this definable normal subgroup, which is a solution set of this formula, and you get something semi-simple. So you get something which has no proper non-trivial abelian normal subgroups, because that's something that you can say in a first-order way. And then it's clear that the soluble radical of a pseudo-finite group, it exists precisely when it's equal to this phi rg, the soluble radical is, which happens precisely when this phi rg is soluble, which is precisely when you are looking at the soluble radicals of the finite groups, and you're asking when there's a uniform bound on the solubility degree of those guys. And so now this is telling and suggesting that when you study pseudo-finite groups, you can do it in 2 blocks. So you can either study the pseudo-soluble part, where you know that you are an elementary equivalent to an ultra product of soluble groups, and you ask whether you are soluble or not. Or you can look at the semi-simple part and just ask how does it look like? What is the structure? And both are studied by different people. So First of all, I wrote here this result by Coukreau, which is saying that if the centralizer dimension of a G is K, so if there exists some K, so that the longest proper chain, descending chain of centralizers has length K, then the soluble radical exists. And this, of course, in particular, contains stable groups, which are independently proven to have the soluble radical in the pseudo-finite case by McPherson and Tent. Then there is this result by Milliet from 2013, which is saying that if you have a super simple group, if G is super simple, then the soluble radical exists. And then I just needed to mention what we also noted with Frank is that if G is finite dimensional, then the soluble radical exists. But I should say that it's not a generalization of Milliet's result. Milliet doesn't use the super simple of finite as you rank here. We have really in the finite dimensional case. But it's something that we needed to observe to be true because we didn't want to use we cannot use the classification of finite simple groups. Okay, and then going to the semi-simple part of this study, there are again several results. So there's a result from 2012 from McPherson and Tent, who proved that if your group G is NIP, then when you cozen out by the soluble radical, when you cozen out by the definable subgroup phi RG, then you get something finite. And so in the earlier paper, they proved that in the stable case, I already mentioned the stable case, since the soluble radical is actually soluble, it just means that G is soluble by finite. But in this paper, they showed that in the NIP case, there are counterexamples. There are examples where the phi RG is not soluble, so they cannot conclude that this G is soluble by finite. Then there is a result by Milliet from 2013, which is saying that if G is super simple, then again, when you're looking at G bar, it has a definable normal subgroup L bar, which is a finite direct product of simple finite or pseudo-finite groups. And moreover, when you cozen by that, then you are finite by abelian. And very similar construction by myself later on when you bound the centralizer dimension. One of the main, but perhaps the only main difference is that in the case 3, you can also say that this G bar, L bar really can't be infinite, whereas in the super simple case, I think you can actually say that this is finite by killing the field automorphisms. I believe so. And then the fourth note is here just to kind of show that if you want to get more, if you want to say that this L bar is actually simple and zero definable and stuff like that, you need more assumptions. This result is just something that we really needed in the particular situation. So it's an example here of the situation where you get the L bar, the SOCL, to be simple and zero definable. So if you add assumptions to the centralizer dimension such that any subnormal subgroup actually is centralized trivially, then you get a simple definable subgroup, so a Chevrolet group of G, so that again the quotient is finite by abelian, but you cannot say that it's finite. Okay, so all of these 1 to 4, they essentially have the same strategy of proof. The proof is always more or less the same. So the idea is that so you go to this semi-simple quotient, and then you are looking at the SOCLs of the finite groups in the ultra product. So Nick was defining SOCLs earlier in the finite group. It's just a group generated by all minimal normal subgroups. It's well defined in the finite group theory. And then you are asking, because you have this direct product of some Li many for each of the Gi, and you're asking that can you bound this Li, the number of the components, independently from I, not depending on the finite group Gi. And if you can, and you can if you are in the super simple or finite dimensional stable, or if you have things like centralizer dimension assumption, if you can, then you just go to the pseudo-finite level, and you are going to find this definable normal subgroup, which is a finite direct product of simple pseudo-finite groups. And then if you happen to be in the NIP, in the stable, in the kind of place where you cannot interpret the pseudo-finite field, then you just get a contradiction and you get that this G bar is actually finite. Whereas if you are somewhere where you can interpret the pseudo-finite field, then you get the type of results as 2 to the 4. And you get the structural results. Okay, and so I wanted to highlight, and I wanted to kind of give this kind of overview of what people have been proven. Also to say that now 1 and 4, how I just explained that they are proven, they heavily use the classification of finite simple groups. And similarly, the Wilson's theorem uses a classification of finite simple groups. So to my understanding up to now, the results on pseudo-finite groups, at least almost all results on pseudo-finite groups, which don't use the classification of finite simple groups, they are just to prove, for example, that the soluble radical exists for some restricted class of groups. And so that led us to the question that we wanted to study. So there is this paper Elf-Chalicot, McPherson-Rutten that Nick also mentioned already. So it's the paper where they proved the pseudo-finite super simple analog of Rosowski's result on definable actions on strongly minimal sets. And so they ask precisely that if you are given a super simple of finite SU rank, simple as a group, pseudo-finite group, whose SU rank is 3, can you prove that it's PSL2 over a pseudo-finite field without using the classification of finite simple groups? So as I said earlier, Wilson's result does tell you that this is true. This is true if you use the classification of finite simple groups. And in general, what can you prove? What can be proven without the classification of finite simple groups? And that's what we started to study with Frank. So now let G be a pseudo-finite finite dimensional group. First of all, kind of what is known, but was already proven in the paper by Frank, where he defined finite dimensional groups. So first he proved that if the dimension of G is 1, then your group is finite by abelian by finite, which is something very not surprising, and something that is proven in a similar setting. So this agemr, Elf-Chalicot, McPherson-Rutten, they did it in the context that Nick was already giving before. So it was a super simple of finite SU rank with some extra assumptions. There is this result by Hempel and Palasin on pseudo-finite groups, where they in particular observe by the end of it that the pseudo-finite super simple finite SU rank implies finite by abelian by finite. There are things by, I think, perhaps Elves and Rutten, or perhaps Chalicot and Rutten, I forgot, on the measurable, when you add measurability assumption. But essentially, when you have something finite dimensional or super simple of a SU rank 1, and then you add some extra assumptions, strong extra assumptions, it's often proven that you get finite by abelian by finite, whereas in general, it's a very big open question. Okay, so this is something we are going to use throughout, that we know that dimension 1 in our setup always gives us something finite by abelian by finite. And the second result by Frank in this paper was that if the dimension is 2, then G is actually soluble by finite. But in the paper, he uses the same proof that I already mentioned a couple of times. So he used the same proof. He says that, okay, you quotient out by the soluble radical, and then if the soluble radical is not of finite index, then you get something of dimension at most 2, and then you find the definable Chevalier group, and hence the dimension must be at least 3, and hence you get the contradiction. So he used the Wilson's result, and so what we proved are these two results. So the first one says that if you have a pseudo-finite finite dimensional group whose dimension is 2, then the group is soluble by finite. And moreover, if it's not finite by abelian by finite, then there is a definable subgroup N of G with the dimension 1. And so here I wrote the Wagner / Karhumäki-Wagner because this is a result that Frank already proved earlier and never published, but it was known. But our proof is very different. So what Frank did, there was lots of, at least partially, it was a computation on the independence notion. And what we are going to do here in the dimension 2 case is essentially the original proof, but by showing that you don't need classification of finite simple groups there. And by that I mean that we say that, okay, if you are not soluble by finite, then we show how the involutions in the group behave, and then show that they behave exactly as in PSL2, and then use a result from finite group theory showing that, again, you have a definable Chevalier group, this time PSL2, inside, and get the contradiction on the rank. And that to be said, our main result is that this theorem 1.10, if G is a pseudo-finite finite dimensional group of dimension 3, then either G is soluble by finite, or when you take the almost center and you quotient by that, so the almost center is finite and you quotient by that, so you can get something of dimension 3, that has definable normal subgroup of finite index isomorphic to PSL2 over a pseudo-finite field F. And so that in particular, of course, answers the question by Elf, Chalicot, McPherson, and Rutten. So yes, you can say independently from the classification of finite simple groups that a simple pseudo-finite finite dimensional dimension 3 group is PSL2F. And And the fun thing about these theorems, or a thing maybe, well, fun, I don't know. Well, the thing is that the proofs of these theorems is essentially the same. So in the theorem 1.10, it's longer, it's more complicated. There are more steps that you have to do. But the idea in both of them is the same in the sense that what we are going to do in both of them is that you say that, okay, if you're not soluble by finite, then we are going to study the involutions in the group so that they behave as in PSL2, then recover PSL2, and in the theorem 1.9 you get the contradiction, and in theorem 1.10 you get PSL2. So that to be said, for the rest of the talk, I will try to more or less overline at least the last game of involutions of how to get PSL2 in both of these cases and thus recover both of the theorems. Good. Yeah, okay, so then there is this one question that I think, well, obviously follows from theorem 1.10. Could you also drop the assumption that the simple pseudofinite group actually is finite dimensional? So could you also prove, without the classification of finite simple groups, that a simple pseudofinite group is finite dimensional? That's something to think about. Good. So let's go to the results and the proofs. So the proofs and the tools. What do we use? What do we need to prove our things? So first, I have to say something about what do we use from finite group theory, since we are doing results without classification of finite simple groups. And so, well, first of all, we use Veit-Thomson. So we use the fact that a finite group with no involutions is soluble. And so it's, to my understanding, one of those results which was one of the first like very long proofs in the finite group theory, but which actually today, to my understanding, is like 50 pages and computer proved. And the second, the main tool put together, here are two theorems from finite group theory put together in this theorem, and this is really the result that we use to identify PSL2. So what does it say? So let G be a finite, simple, non-abelian large group. If one of the following two conditions hold, so one of the two that I will read soon, then what you get is that your group G is a Chevalier group X over a finite field FQ, where the X comes from this finite list PSL2, PSL3, PSU3, and Suzuki group. And the large, of course, just means that here I'm gathering together two results from finite group theory, and in both of them there are kind of finite list of exceptions, and the large means bigger than any of those finite list of exceptions. Okay, so what are these conditions that need to be held? The first one is that the M2 rank of the group is at most 2. So what does it mean? It means that if you take 3 involutions, J, K, and L, so IG always means the set of involutions of my group. So if I take 3 involutions, J, K, and L, which are distinct and pairwise commuting, then I have that JK is equal to L. So what does it mean? It means that the maximal elementary abelian subgroup is of order 4. So it's a Klein-4 group. Okay? Clearly something that you can say in the first order way. And this is a result I wrote here, Gorenstein and al. The main part of it, I think, is that Gorenstein and Walter, they proved that a finite simple group whose Sylow 2 subgroups are dihedral is PSL2. That's kind of the longest part of it, but the whole thing, this N2 smaller than 2, N2 G smaller than 2, smaller than equal to 2 theorem is in Gorenstein's book in like 70 pages. And the second part of the conditions is that you don't have a strongly embedded subgroup. So what does that mean? A strongly embedded subgroup is a proper subgroup C of G, such that this proper subgroup has involutions, but whenever you take an element G outside of this subgroup C and you conjugate, the intersection has no involutions. So again, something that you can clearly say in the first order way, and thus you immediately get this corollary that if you're looking at a semi-simple pseudofinite group who is finite dimensional and the dimension is at most 3, this is the situation that we want to be all the time, well then, first of all, there are involutions. This is just Veit-Thomson, so there will be this so-called in this semi-simple group and the so-called in each of the components in the so-called involutions. And furthermore, if you can prove one of these first order properties, either that the M2 rank is very small or that your G has a strongly embedded subgroup. And here I really mean by strongly embedded subgroup a definable subgroup which is elementary equivalent to the outer product of the strongly embedded subgroups of the finite group GI. Then what? Well, then you are going to find the so-called the definable subgroup PSL2. So that means that you are going to find a normal subgroup PSL2 over a pseudofinite field, but that must have dimension 3. So that forces the whole group to have dimension 3 and shows that this PSL2 subgroup that you find, it's a normal finite index subgroup. And so it's a direct consequence. So this is really what we want to prove. We want to take a finite dimensional group of dimension at most 3, and we want to show that if it's not soluble by finite, then one of these conditions holds. And in our results, we also need one more result from finite group theory, but in a little bit stronger form than originally. So we also need to be able to say that the centralizers of involutions are big, so they're infinite, so they have a dimension at least 1. And that's something that is known if your group is elementary equivalent to outer product of finite simple groups, because Brouwer and Fowler, they proved that the up to isomorphism, there's only finitely many finite simple groups of given centralizer of involution. But we need a bit more because we are not actually going to work with the definable simple group. We are going to work with something called almost simple group. So we need this generalization of Brouwer-Fowler theorem, also proven independently from the classification of finite simple groups by Hempel and Palasin, which says that if you have a pseudofinite group with trivial almost center, then your centralizer of involutions are infinite. Good. So these are the tools from the finite group theory we need. Then I also want to mention the Schlitzling's theorem, which we use everywhere, and which, well, Nick said it. Someone always says it's Frank's favorite theorem. I've heard it too. So just to kind of give you an idea how we use it all over our proofs, I wrote this slide. So the Schlitzling theorem is here. And well, here is the version of it written by Wagner, which is easier to pronounce. And so it says that if G is a group and you have a uniformly commensurable family of subgroups, then there is a subgroup H of G, which is uniformly commensurable to all members from this family, and which is invariant under all automorphisms which are fixing this H setwise. And so we get things like this for free from the Wagner's version of the theorem 1.15. Well, that's both theorem 1.15. So first of all, an infinite group is called almost simple if it's not abelian bifinite and has no definable normal subgroups of infinite index. And now it's easy to verify the following. So take an almost simple group that has the ICC 0 condition, i.e. where the almost operators are of definable subgroups are definable. A follows immediate, it's just immediate corollary of this theorem 1.15. If H is an infinite definable subgroup of infinite index, then it cannot be almost normalized by G because of the dimensions. And the second one almost immediately follows. So you have to note that almost simple implies trivial almost center, and it implies semi-simple. And then it's easy to see that, okay, if you have an infinite definable soluble by finite subgroup, then the almost normalizer actually has to have infinite index in G. And in particular, you can say things like, if G is pseudofinite, finite dimensional of dimension at most 3, and you get a proper subgroup of dimension 2, which is not almost normalized by G, then either this subgroup has a trivial, has a finite almost center, or the original group had an infinite almost center. And so why would I write something like this? Is because the main biggest difference between the rank 2 and rank 3 theorems are that in the rank 3 theorem, we have to analyze the subgroups of dimension 2. How do they look like? And so this is telling us that they are going to have finite centers and the finite almost centers. And the next slide is going to be a long and technical slide, but bear with me, I will read through it. I just want to give you a feeling that we do prove that the rank 2 subgroups in the dimension 3 case are up to commensurably as they should be. So now I'm having a long slide. I will read you through it. I won't talk about the proofs, but I will describe this slide. Okay, so we have an almost simple pseudo-finite finite dimensional group, and this time we assume that the dimension is 3. We want to say that the dimension 2 subgroups, we want to think that our G is PSL2 up to finite index. And so we want to say that our rank 2 subgroups look like the Borel subgroups of PSL2. So they look like the semi-direct product between the additive part and the multiplicative part. And we both want to say that, and also that it behaves like the Borel subgroups in PSL2 in terms of intersections of conjugates, in terms of involutions, and so on and so on. And all that we do up to commensurability. So we do assume that all definable subgroups of dimension 2 are soluble by finite, just because we are going to apply the rank 2 theorem. And then, okay, so let L be a definable subgroup of dimension 2. Just repeatedly applying the almost operators, taking first B to be the almost normalizer of L, we get that we have a maximal definable subgroup of dimension 2, which is self-almost normalizing, and in particular, as what I said in the last slide, with the finite almost center. And the finite almost center is something that we struggled quite a bit at some point. So from the very beginning, we kind of wanted to follow the steps of Serling in the classification of rank 3 groups under the assumption that there are no bad groups, and kind of build the P-n pair and look at the Borel subgroups and so on and so on. But we struggled with this thing that this finite center is finite, and you cannot kill it because you're doing things up to commensurability, so you cannot talk about the finite a little bit. But okay, then we didn't care. Then we continued with it being finite. But so you find this maximal dimension 2 subgroup, which has a finite almost center. And when you quotient by the almost center, you get what you'd like to get. So you get this U and T, so the unipotent part and the toral part, which again you define using the almost operators, but otherwise as you would in the Borel subgroup of PSL2. So the U would be the centralizer of itself, and the T would be the centralizer of itself in the normal setup. And here you take the almost operators. And when you quotient them by the finite center, you get what you want. So this U is up to commensurability isomorphic to the additive part of the pseudo-finite field. So you have to do a field interpretation result here. And then when you quotient the toral part, it embeds as a finite index subgroup to the multiplicative part of the field. And in particular, what that means is, moving to this part 3 here, it means that if this B contains involutions, so if this Borel subgroup B contains involutions, either there are some in the unipotent but not almost center part, like in the case where you're in the PSL2 and the characteristic of the field is 2, and then there are actually infinitely many. Then actually the whole U set is just an infinite elementary abelian 2 subgroup. And when you quotient the B with the conjugate, we check that as in the usual case, you end up, this doesn't point at all. So when you're looking at the quotient, you end up to the subgroup of the toral part. So that just means that if there are involutions in the unipotent part which are not in the center, then the Borel subgroup is strongly embedded subgroup. Hence, we are done because we are looking for PSL2. So what 3 is saying that if B contains involutions, then either it's strongly embedded or there is an involution in the toral part. And that's really saying that there is an involution in the toral part, which is not in the center, and its centralizer has dimension 1. So that's the fourth part. The fourth part is saying that if you take X from my Borel subgroup, who has a rank 2 dimension, then actually it belongs to the almost center. Again, as in the PSL2 normally. So I still want to say about the involutions. The 3 says that either you are strongly embedded and there are involutions in the unipotent part and not in the center, or there is an involution in the toral part with dimension 1 centralizer, but there can still be involutions in the almost center too, which is really something that we also tried to kill for some time, and it wasn't so easy. So even if you have you find these correct involutions from the toral part.
You say something about the case where B has no involutions? Can you just say something about when B has no?
Yeah, because I mean, if B has no involutions, I don't care. My group G will have involutions anyway. I mean, here we are just what I will later on show you is that you consider the situation where all involutions have rank 1 centralizers, which is going to be a good situation, or if there is one rank 2 involution, then it will live in AB. You know, then there will be a Borel subgroup B where there will be involutions. That's why. Good. So that's kind of long slide, but what you can take of it if you didn't want to listen is that the rank 2 subgroups in the rank T, in the dimension 2 subgroups in the dimension 3 case, really up to commensurability, look and behave as the Borel subgroups in PSL2. Good. So now, in identifying the last game of involutions, kind of identifying PSL2. So what do? We have an almost simple pseudofinite finite dimensional group G, and the dimension is at most 3. So we are going to deal both of the rank dimension 2 and dimension 3 case. And if the dimension is 3, then we let the 2-dimensional subgroups be soluble by finite, because we're going to apply the dimension 2 result. Okay, so the claim is that G is a finite extension of PSL2 over a pseudofinite field. And thus, by what we've seen so far, we may assume that G has no strongly embedded subgroups, otherwise we are done, and that the M2 rank is bigger than 2, otherwise we are done, and that all involutions have at least rank 1 dimension centralizers by the Palasin-Hempel result, and in particular, that if you start with the dimension 2 group, then the involutions have centralizers of dimension 1 by Schlichting's theorem. Good. Okay, then what we are going to set this Cj to be the almost centralizer of the centralizer of involution. So the point is that if you think about PSL2, we really are thinking about the situation where there are no strongly embedded subgroup. So the centralizers of involutions, they should be just the abelian toral part together with an external involution, which is called Weyl involution. So somehow, if that were the case, then this Cj would just be the toral part. But we don't know exactly, because since we only know that things up to commensurability, we again have to work with the subgroups up to commensurability. So we said that, and the first thing we say is that there is an involution with dimension 1 centralizer. And for any such involution, there is another involution. There's a typo. There's another involution, so this K, there's K, so K is again an involution. There's another involution K, which is normalizing this Ci, the almost centralizer of the centralizer of I, but it's not in Ci. And then there's a further part, but maybe you can forget it. I won't have much time left, so I won't be talking about that. And so let me just kind of say verbally why is that the case? So if all involutions have rank 1 centralizers, then again you just take the almost normalizer of the almost normalizer of this Cgi, and you get something of dimension 1. And when you conjugate, when you intersect conjugates, there must be an involution inside, otherwise you have a strongly embedded subgroup. And then involution cannot be in Ci because all involutions have rank 1 centralizers. And if not, then you just apply the last theorem. Okay, so that was not the proof, but claim 1, you can do that. Okay, so then let's have I as in claim 1. And we take the n to be the normalizer of this. Now I'm saying that this K fixes a unique involution in Ci, and for these K and L, these two involutions that we are going to consider, we know the dimension of the centralizers. This is just wash, because n is a finite extension of Ci, so the K and L, the existence of L just follows from Wasch's theorem. It's something that is true in the finite group theory. And the dimensions of these centralizers, it's just last slide. If they are of dimension 2, then we know the structure and we start playing, we start showing that actually K couldn't be as it was found because of the structure of rank 2 subgroups. I don't have time to go into the details of that, but you can do it. And then finally, the fixes the unique involution. The uniqueness also follows from the similar setting. So if there were 2, then you would kind of find an element with the rank 2 centralizer, and you would be in a Borel subgroup where this K and L and I couldn't live in the way that they live, as we've proven. Good. So then we say that now if I have 2 involutions from the CI, where the centralizers have the correct dimension, then they commute. This is, again, essentially WASH. It took us a while to find the 3-line proof, but it's essentially WASH. WASH is saying that in a finite group, any 2 involutions, either they are conjugate or there's a third involution commuting with both. You play with that, and you get that they commute. And similarly, if you have 3 distinct involutions with correct dimensions of centralizers, then you get that they can generate a Klein-4 group. Same reason, just WASH. And then using all that, we proved that actually all centralizers of involutions have dimension 1, as in PSL2. I'm not going to go into details of that. So now we are done. Why? We assumed that the M2 rank is bigger than 2. Now if we take a pairwise commuting X, Y, and Z, so that they don't generate a Klein-4 group, then by above, we know that when we are looking at these almost centralizers of their centralizers, they cannot be all equal, so you have these two cases. Now if you have the former case that Cx is Cy, but not Zz, then this Z lives in the normalizer of Cx, not in Cx, centralizes both X and Y, but we know that it only can centralize a unique involution, so you get the contradiction. And in the latter case, you get the Yz in this Cx, which is centralized by Y, and again, by the uniqueness, you get that actually they did generate a Klein-4 group, which is not true. And then we are done. So I'm also out of time, so let me just say that now you just finish by saying that, okay, if I wasn't soluble by finite, then I apply the identification from last page. We don't have to go through the details of that, so I think I'm going to stop here.
Are there questions, remarks? Yes. Let's start. Okay, let's start at the back.
So thanks, very interesting. I'm a bit surprised that you need some external material to kill the strongly embedded case, because you don't believe in the strongly embedded case, do you?
I mean, what do you mean? You mean that we need the classification from the finite?
So do you have enough Silberstyle generation, indecomposable generation in this context?
Sorry, what? I didn't hear you.
Do you have an indecomposability theorem?
No, we don't. We don't.
Okay.
We don't. No, we don't.
Okay. Well, okay. that.
We did because we first did things in the super simple context, but then we moved to finite dimensional context, and we don't anymore.
Okay. Well, yeah.
So maybe I'm mistaken, but in the dimension 0 is the finite sets, right? And dimension, if you have infinite thing, then you at least dimension 1.
Yeah.
Right? Could you go back to slide 7?
Sure.
Because I was confused there. Maybe it's a greater 7. Yes, at the last one. Because there you say either the almost center is finite or the dimension is greater or equal to 1. Do you mean strictly greater than 1 here? Because otherwise it seems to me that's
either the almost center of H, which is
H and G. Okay, now I get it. Yeah, I'm sorry. I think I didn't see the G.
Yeah,
okay, perfect.
So the point
now
is that
it's
if
clear.
G is almost simple, then you can say that also. Yeah.
Any other questions? Oh, if not, we can thank Ulla again.